All right, everybody. Today we are going to talk about the new chapter, chapter 9, gas power cycle. So, chapter 9, gas power cycle. Okay. So, in this chapter, we'll talk about some of the gas power cycle or some of the cycle that are heavily used in the analysis of any thermodynamic cycle, right? Or to compare any thermodynamic cycle. So, in thermodynamics, we're mostly talking about like thermal events, thermal process, thermal cycle, right? Two most important thing or two most important application of the thermodynamics is the power generation and refrigeration, right? So let me write it. So two most important areas of thermodynamics are: number one is the power cycles, and number two is the refrigeration cycle. Refrigeration now in this power cycle, or you know the power cycle is mostly related for power generation, right? Power generation system. And the refrigeration cycle, we all know that mostly used for refrigeration and air conditioning. Refrigeration and air conditioning, right? Refrigeration and air condition. Now, in this chapter, we'll talk about the power cycle, like some part of the power cycle. In power cycle, it also consists of two different type of cycle, right? So power cycle, it also has two different area. One is gas power cycle, which is this chapter, and another is uh, vapor power cycle, vapor and combined power cycle, combined power cycles. Okay, so these two. Now, in we talked about a lot of closed system, open system in the previous chapters, and we also talked about the thermodynamic cycle, right? So all of those basic definition, but just to reiterate those important term for this chapter, so then whenever I use them in this chapter for the reference, you guys can you know um, visualize those items, right? So for example, engine, definition of engine and power cycle. And power cycle, so uh, basically the engines are those device that used to produce, are those device that are used to produce a net power output, right? And the power cycles are basically those engines follow some sort of cycle, right? The thermodynamic cycle, a thermodynamic cycle. A thermodynamic cycle, the engine engine follows or operate, right? So similarly, in the refrigeration cycle or refrigerator, basically refrigerator is a device that produce cooling effect by consuming sort of work, and refrigeration cycle is basically the cycle that a refrigerator works or follow, right? So those sort of thing, just to keep you like bring those memory back. In the thermodynamic cycles or thermodynamic events. So since this chapter is basically that gas power cycle, so we'll talk about the gas cycle. So what is gas cycle? If the working fluid of a cycle working fluid of a cycle is in gaseous phase, if the working fluid of a cycle is in gaseous phase throughout the entire cycle, throughout the entire cycle, then it's a gas cycle, right? So this is important. In gas cycle, the working fluid will remain in the gas phase. However, if it is a vapor cycle, the working fluid will be in vapor phase. Working fluid can be in vapor and or like other phases too, right? Gas phase, gaseous phase. Imagine that water, it can be superheated vapor, it can be in that gaseous phase, or it can be liquid or saturated liquid phase. So that's the difference between the gas cycle and the vapor cycle. And let me highlight it. So we basically defined the gas cycle and the vapor cycle. So let's just go ahead and start talking about those the topics that is related to the gas cycle, where this gas cycle is used, right? So where this gas cycle excuse me, gas cycle is being used, right? So imagine that any diesel engine or spark ignition engine or internal combustion engine, it not only just the fuel, right? You need some sort of like air mixture as well to complete the combustion. So all sorts of like internal combustion engine, they're using using this type of gas cycle, right? So all internal engines or IC engine, internal combustion engines, internal combustion or IC engines are using the gas cycle or follow the gas cycle, right? So now let's talk about the basic steps or basic consideration of operating or analyzing a power cycle, right? Or like the gas cycle. So what are the key things, or what are the key component of a gas cycle? So we'll talk about in this topic, which is 9.1, basic considerations in the analysis of power cycles. So in power cycle or a thermodynamic cycle, we saw in previous classes that if it is a PV diagram, right, and if this cycle, if it is a thermodynamic cycle or operating in a cycle, then it will have initial and final state will be same, and the process will be a cyclic process, right? So let's just consider a cycle that operates like this way, right? So this is just a ideal case. Imagine that you have starting point. Let's say you have a starting point right here. This is 1, this is 2, right, and this is 3, and this is 4, meaning that it's going from 1 and then going from 2 to 3, 3 to 4, and it's again coming back 4 to 1. This is ideal case, right? So if there is no loss or no irreversibilities, then this is the ideal case. However, in actual case, we saw a lot of losses or irreversibilities. So in that case, they don't really follow this straight path. So in that case, they follow some sort of like deviated path, right? So if I draw a deviated path, it will be like this. Rather a straight line, it will be like this. So this is a deviated path. So this is actually actual or real actual cycle, right? And this one is the ideal cycle. So what is the importance now from this one? You can see that if you have some sort of ideal cycle or standard cycle, then you can compare your device, that how much is efficient or how much is how good is that device, it's working compared to a standard. So we need this sort of ideal cycle just to compare or to measure the efficiency of an actual cycle, right? So in actual device or actual cycle, actual device always follow actual cycle, right? Actual cycle, or vice versa, actual device produces the actual cycle. In actual cycle, there are so many complexities, right? So those complexities, for example, due to the friction, right, or due to the pressure loss, or due to the it cannot reach the inability to reach in equilibrium, right? Equilibrium. So these are the complexities associated with the actual cycle, right? So to keep these complexities in manageable level, the concept of ideal cycle came out. So if we have ideal cycle, then we can compare, or we will see that what are the devices is actually not giving us their best or not giving us their 100% of their efficiency. So we can find out, or we can figure out, and then we can basically minimize those effects, right, or those losses. So if it is for for thermal cycle or thermodynamic cycle, we know that the thermal efficiency, eta thermal, equals to W net divided by Q in, or we can write it in terms of mass. So W net, small w, and Q in, right? Excuse me. So now in ideal case, right, so if we look at this diagram, in ideal case, we see that there is no pressure loss, or there is no friction, and everything, all of those components of that system is following the straight path, right? So that means if the efficiency of an ideal cycle will be 100%, that's for sure, right? However, for ideal cases, we have to consider some assumption as well. So for ideal cases, assumptions are number one is that there is no pressure drop, pressure drop or no pressure loss, right? Or cycle doesn't have any friction, no friction, right? So number 2 is that expansion and compression takes place in a quasi-equilibrium process, which is quite impossible. Expansion and compression happens in quasi-equilibrium manner. And number 3 is that like all of the pipes connecting like devices, for example compressor, turbine, pump, all of those devices are connected in a system are oil insulated, right? Pipes are oil insulated, that means there is no heat transfer or no heat loss. There is no heat loss, right? So that's the condition, or those are the assumptions for ideal case, right? So however, in actual case we see a lot of drawbacks, or we see a lot of actually losses, and we see the difference between the ideal and actual. There are some, I mean, we can see those losses by just by taking a look at the diagrams. So now from now we'll talk about so we've just talked about the ideal cycle, but let's name the ideal cycle. What could be the name, or what could be the ideal cycle that is standardized by the thermodynamic community, and then they use that cycle for their reference to solving real life problem, right? Or to analyze like real life application. So one of the cycle, or the name, ideal cycle name, is that Carnot cycle. So 9.2 Carnot cycle, and its value in engineering. Value in. So this topic itself is saying that it's very important having the knowledge of Carnot cycle, and it will help you to analyze a lot of cycles that involves thermodynamic process or thermodynamic event, right? So the Carnot cycle, it's also an ideal cycle, right? So imagine that you have a thermodynamic cycle or thermodynamic system that has some devices. For example, let me draw it. So this is a this is a turbine, and then so in the turbine compressed vapor or compressed gas is coming, and then output of that turbine is going to another turbine, right? So if we have another turbine, the output of this turbine is going to this one, right? And then which is basically the input for this turbine, and output is this turbine is going. Once multiple expansion is happening, then it's going back to a compressor. So compressor is basically compressor, and then from that compressor we have another compressor, right? So the output of this compressor is coming as a input of this compressor, right? And then the output of this compressor is basically the input of this one. And important thing is that both of the turbine is connected in this single shaft, right? and both of these compressor is connected in this single shaft. All right, so now what is happening, so let's consider state 1 is here, starting here, and then this is state 2, and this is state 3, and this is state 4, right? So what is happening here in the isothermal turbine, so this turbine is isothermal turbine, and this turbine is isentropic. Similarly, this is isentropic compressor, and this is isothermal turbine, right? So let me write one more thing. So in isothermal turbine, heat is input, Q in, right? And in isothermal compressor, heat is output, Q output. And then this isentropic compressor, it's producing the work, W net. And yeah, I think that's all. So components of Carnot cycle. So assumptions, there are some assumptions for the Carnot cycles as well, right? So number one assumption is that isothermal heat addition, the heat addition to the turbine, it has to be isothermal. Or not assumption, you can tell another assumptions, or you can tell that the components of Carnot cycle, right? Number one is that isothermal heat addition, and number two is isentropic expansion, which we saw that in the bigger turbine, which is this one, right? Expansion. And number three is isentropic compression, actually it will be isothermal, yeah, isothermal compression. And number four is isentropic compression. Okay. So now if we draw a PV diagram from this cycle, remember this is state 1, state 2, state 3 and state 4, then we'll get two different then we'll get the diagram of PV diagram, which is, this is PV, and let's say we will draw the TS diagram as well. This is P versus V and T versus S. So it's saying that the first one is so the first one in the PV diagram, it says that isothermal heat addition, that means temperature is constant. So if we look at this TS diagram, it will be isothermal heat addition. So isothermal means that straight line, and this will be horizontal line. And then in PV diagram, that isothermal line will be from, let's say, from here to here, right? So basically it will look like this. And then from 2 is isentropic expansion, right? So the isentropic expansion, if we consider this one isentropic expansion, it will look like a vertical line. So this is 1 and this is 2. 2 to 3 is basically isentropic expansion. So expansion means that volume is increasing further. So isentropic expansion will look like this, right? So this is 1, this is 2 and this is 3. And then number 3 to 4, when it's going 3 to 4, then it is isothermal compression. So if it is going through isothermal compression, then the isothermal compression means that again it will be a horizontal line, right? This is 4, and in here compression volume will decrease eventually, so it will like this, so it will be 4. And 4 to 1, it's basically isentropic compression again. So isentropic compression is this, right? Entropy is constant in this line. So this cycle is now is happening this way, and then 4 to 1, it's this, right? So this is how this cycle is operating, right? So from this diagram, TS diagram, we can see that 2 isothermal, right, which is these two. Let me use different color for isothermal. These two are isothermal, right? And basically this one isothermal, and this one is isothermal, and these are these are actually these two are isotropic, and these are the isothermal. So isothermal and isothermal, right? Means that isothermal, and this means that isentropic. Okay, so now we have the PV diagram and TS diagram, and we also know that, I mean, we can see from this diagram, TS diagram, everything is pretty much straight line, right? So in this case, it's ideal as well. Obviously, the Carnot cycle is an ideal cycle. So ideal cycle efficiency of the Carnot cycle will be efficiency of the Carnot cycle, thermal efficiency of the Carnot cycle, Carnot equals to 1 minus low temperature reservoir and high temperature of the high temperature reservoir. So that means that Carnot cycle operates between a low temperature reservoir and high temperature reservoir, which is source versus sink, and then it has the efficiency which is equals to 1 minus TL divided by TH, right? So the thermal efficiency for this expression, it's basically telling us that if a, or like the Carnot cycle operates between the thermal reservoir, two thermal reservoir, one is the source and another is the sink, and the thermal if the thermal efficiency increase then the average temperature at which the heat supplied to this system is also increasing. So those sort of information we can conclude from the Carnot cycle. But however, keep in mind that so these are our standard cycle. When we do analysis the actual cycle, we'll again plot them, and we'll try to see that how the actual cycle is deviating from this ideal cycle. So that's the use of the Carnot cycle. So now to analyze the Carnot cycle, since the chapter is dealing with the gas phase, right? So we need to assume, or we need to consider some sort of characteristic property of the air, right? So what are those characteristic properties, or what are the assumptions we are taking in place to consider for an ideal cycle, right? So that would be 9.3 air standard assumptions. So some of the assumptions, I would like to bring one example here. So let me copy this one. Cut. Actually, let's put it here, and then let's just take it in this one. All right. Okay, so I took this one from How Stuff Works website, right? Basically, to show you guys, it's a diesel cycle, right? Diesel engine. Let me write it. Diesel engine. And in this diesel engine, you can see multiple things is happening. So you have the compressed air is coming, you have the fuel, and you have the air intake, right? So you can see just right now its air is intaking, and then it's burning, and then it's leaving or exhaust, right? So that means that this diesel engine has the air circulation, or this diesel engine following some certain type of cycle, and that cycle involves the air, right? So we have to consider some sort of standard assumptions for those years. So what are those standard assumptions? Number one is the working fluid, or the air standard assumptions. The working fluid is air, right? So this is number one assumption, which in case of the closed loop or closed cycle, and it always behaves as ideal gas, right? Number two, all the process, like all those processes happening here are internally reversible. All the process are happening and then combustion process, it's basically the heat addition process from an external source. Basically the combustion is happening, and it's kind of heat addition to this system, just by burning those hydrocarbons. So combustion process is replaced by an external heat addition process. And the number four, the exhaust process is replaced by a heat rejection. Actually it will be heat source and heat rejection, which is sink, right? Heat rejection process that helps or that restore the initial state, right? So these are the standard assumptions for the air. Now when these assumptions are utilized, or standard air assumptions are utilized, we also call them cold air standard assumptions, also known as cold air standard assumption, right? So that's all about those air standard assumptions that we use in any sorts of like actual cycle combustion chamber, right? um, and to analyze this type of cycle or actual cycle, we need the ideal cycle, right? So that means that we have to use Carnot cycle. We'll use this Carnot cycle multiple times. So that's all about this class. We'll go ahead and solve some problem based on the standard cycle, which is the Carnot cycle, and we'll try to see that, whether the efficiency is coming 100% or not. Thank you for watching this video. We'll come back with the math problem. Thank you.